In this tutorial, we will look at how ions are formed and how they make compounds. So to start, let's look and get a couple of examples of atoms from the periodic table. Maybe we'll take a look at calcium, which is number 20, and we will look at fluorine, which is number 9. So let's draw the Lewis structures, the Lewis dot diagrams for those. Calcium, which is in group 2, so it has 2 valence electrons. So there's the Lewis dot diagram for calcium. Fluorine is in group 17, and it has 9 electrons to place. So you could go about it by doing the Bohr diagrams and then doing the Lewis dot diagram from there. But at this point, let's assume that we all understand how to make the Lewis dot diagram from the position of the periodic table. So it has 7 valence electrons because it's in group 7. So fluorine would look like this. And all of the elements on the periodic table want to have full rings. It is the most energetically stable arrangement for any atom to be in. The only problem with that is that the noble gases are the only ones that do have 8 electrons around their outer energy levels or their valence shell. So calcium, in this case, will try to do whatever it can to make a full outer ring. And if you recall the Lewis structures, this Ca is the nucleus, the protons and neutrons, but it's also those inner shells that are already full. So calcium has 2 electrons and has a great tendency to throw those 2 away and form this stable arrangement and fall back on that inner ring that's just inside these 2 valence shells to make it full and therefore stable. Fluorine, on the other hand, has 7 electrons and would do anything to grab just 1 more to make it a stable arrangement. So these are called ions when they do that, because calcium, which has 20 protons, has 20 electrons in its neutral atomic state, and when it becomes an ion like this, calcium has a +2 because it gives away. In other words, it still has its 20 protons. It must, because it's calcium. If it doesn't, it's something else. So it still has its 20 protons, but its 20 electrons are now -2. They actually gave away 2, so that makes 18 electrons. And so if you look at the charge, you actually have 2 more positively charged particles, subatomic particles, than you do negatively charged subatomic particles. So that gives us a 2+ charge. And so we draw that just by putting calcium 2+, or, calcium 2+ like that. Fluorine, on the other hand, fluorine has 9 protons and 9 electrons in its regular atomic neutral state, and that gives it its charge of 0. And again, it's not quite as happy as it could be, because if it received that 1 electron, it would have this full arrangement around the outer valence shell, and it would get a -1 charge. So let's explain that. 9 protons still, but you picked up an electron, so instead of 9 electrons, you actually have 10 electrons. So that gives you a 1 more negative charge, and that gives you a -1. It's written like this, fluorine with a -1. Okay, so now that we understand how these form ions and how metals have a tendency to throw away those electrons because they have fewer than 4, and non-metals have more than 4, and so they're kind of closer to having a full ring, so they have a tendency to gain electrons to get a full ring. Well, these two in conjunction with each other is perfect, because calcium, which wants to throw away, there's fluorine, which wants to take. And so on the test, you're going to be asked a question about showing your understanding about how elements form compounds, and this is one of those examples. So let's just try to go through it. Let's draw the Lewis dot diagram again for calcium. And we'll draw one for fluorine. And actually, maybe I'll do that a different color so that we can kind of follow the electrons as they come through. So there's fluorine. And I'll draw maybe green to show the movement of electrons. So there's calcium and there's fluorine, and calcium would love to give away one, and fluorine would love to get one. And so this type of arrangement happens. But calcium has two, and it wants to give away the other one as well. So how can we fix this if we just have a bunch of calcium and a bunch of fluorine? Well, the obvious answer would be to how about just grab another fluorine? So let's, with 7 valence electrons, and then calcium can throw its other electron onto this fluorine. And when all of that happens, you're left with calcium with the +2 charge, and a fluorine over here with a -1 charge, and another fluorine down here with a -1 charge. And overall, these things have a charge that is equal to 0. And one of the fundamental things we need to remember is that all ionic compounds have an overall net charge of 0. And that's satisfied here with calcium having +2 and 2 fluorines each with a -1. And we write that because you don't want to keep doing this, every time I'm asking you to put 2 elements together. You don't want to do this all the time. It would be a good place to start. But we draw this like this, CaF2. And this 2 indicates that there are 2 fluorines. Okay, and so there's kind of understood to be a 1 here, so you don't need to draw the 1. You can at first, kind of, if it makes you feel, if it helps you understand it, then you can put the 1 there, but later we'll drop that. And so we have this compound, CaF2. I'm going to try just another example here to help you. Let's draw aluminum and sulfur. Aluminum, if you recall, let's jump over here to the periodic table. Aluminum is in group 13, so it has 3 valence electrons. So let's go back over and we'll draw 3 valence electrons on aluminum. 1, 2, 3. And sulfur is right here. It's number 16, and it's in group 16. And it has how many valence electrons? 6. So let's go back here, and we'll draw 6 electrons. 1, 2, 3, 4, 5, 6. And again with the arrows, each of these atoms wants to be stable, wants to have a stable outer arrangement, so that means 8. Aluminum has 3. It would love to give away 3, so it actually gives away 2 to sulfur because 2 is the limiter here. It really just needs 2. So sulfur then becomes, stable. Aluminum, not so much. Still not happy. So we can fix that, hopefully, by throwing in another sulfur. So here's another sulfur. And there's that 1 electron that goes down, but so now aluminum is happy, but now sulfur down here is not so happy. So again, we have to fix it. We can't leave it. The overall charge has to be 0. So solution is to bring in another aluminum. I know this seems like it will never end. Aluminum will donate another 1 to sulfur, and okay, so now sulfur is happy in this arrangement. Aluminum, not so much, so let's fix that. And we'll keep bringing in the other element until everyone is completely satisfied, and you'll see that aluminum now is happy, and sulfur also is stable, has a stable arrangement. So what we can do is we can just look at this, all of it together, and see, what is this? Just like we did up here with the calcium and fluorine, we're going to do down here with the aluminum and sulfur. And so let's just kind of look and see how many aluminum we have. Well, there's 1, there's 2 aluminum, and so that is represented by Al subscript 2. And let's check sulfurs. We have 1, 2, 3. So that's S3. So in this compound of Al2S3, we know that there's 2 aluminum and 3 sulfur, and that gives them all a stable arrangement. They can all become more stable just by accepting or donating electrons. Overall charge of 0, and so we have a compound called aluminum sulfide. And we'll talk about naming in the next tutorial. Try a few of these. Try them this way to show the understanding of how ions are formed and how electrons are transferred in ionic compounds.